Imagine taking inventory of the entire universe, a task of unimaginable scale, counting every single star, each and every planet, and meticulously accounting for all the matter that's fundamentally made of atoms. It's a cosmic census of epic proportions. You then compare what you see through your telescopes and instruments to what the Big Bang's afterglow, that ancient light from the early universe, predicts should exist today. This afterglow serves as a blueprint, a theoretical expectation for the amount of ordinary matter in the cosmos. But here's where the puzzle begins. The numbers simply don't match up. A significant portion, almost half of the ordinary matter, the stuff that makes up stars, planets, and us, is mysteriously missing. This wasn't just a minor error in calculation or a slight discrepancy. It was a gaping hole, a massive void in our understanding of the universe and its fundamental composition. The Big Bang theory, the cornerstone of modern cosmology, predicted a specific measurable amount of baryonic matter, the normal matter we can see and interact with. Yet, when astronomers pointed their most powerful telescopes towards the heavens, they only found about half of what was expected. Where was the rest of it hiding? What could possibly account for this cosmic discrepancy? This perplexing situation became known as the missing baryon problem, and it fundamentally challenged our established theories of how the universe evolved from its fiery beginnings to its present state. It was like trying to finish a complex and intricate puzzle, but discovering that half of the pieces were inexplicably gone, vanished without a trace. Without accounting for this missing matter, we simply couldn't construct a complete and accurate picture of the cosmos. Our understanding remained frustratingly incomplete. Galaxies, those vast islands of stars, weren't just floating in isolation. There was something unseen, something invisible, subtly connecting them in a vast cosmic web. The urgent search for this elusive missing matter quickly became a central and defining quest in the field of astrophysics. If this matter was truly and irrevocably absent, it would force us to fundamentally rethink everything we thought we knew, starting with the very foundations of the Big Bang theory and extending to our models of galaxy formation and the large-scale structure of the universe. Perhaps the universe was simply guarding its secrets more carefully than we had previously anticipated. The missing matter wasn't just a simple accounting issue, a mere discrepancy in our cosmic inventory. It represented a profound test of our fundamental understanding of the cosmos and its underlying principles. Driven by an insatiable curiosity, astronomers meticulously scoured the vast expanse of the universe, absolutely determined to find what had been seemingly lost, to unravel this cosmic enigma. The answer, as it turned out, wasn't to be found within the bright and luminous galaxies, but instead, lurking in the vast, seemingly empty and dark spaces between them in the intergalactic voids. The universe, it seemed, was deliberately holding out on us, keeping its secrets closely guarded, and we, as scientists, were more determined than ever to solve this profound mystery and reveal the hidden truth. The relentless search for the missing matter would ultimately reshape our entire view of the cosmos, forcing us to reconsider our place within it. It was, in essence, a hunt for the very fundamental substance of existence, for the building blocks that make up everything we see and know. And the eventual solution would reveal a universe far more interconnected and interdependent than we could have ever previously imagined, a cosmos where everything is linked in a delicate and intricate balance. Imagine trying to find something incredibly important, something that makes up a significant portion of everything around us. Where do you even begin to look for something that makes up half the universe, yet seems utterly invisible to our current methods of detection? Scientists meticulously searched galaxies, examining their structures and compositions, hoping for a clue. They analyzed gas clouds, probing their densities and temperatures, searching for anomalies. They even investigated the halos around galaxies, those faint, extended regions of diffuse matter, leaving no stone unturned in their quest. But after countless observations and complex calculations, nothing added up. The expected amount of matter simply wasn't there. The universe was winning at this grand cosmic hide-and-seek, concealing its secrets with remarkable skill. The missing matter, they suspected after years of research and debate, wasn't lurking in the form of cold and dense clumps as initially hypothesized. Instead, it might exist as a super-hot, incredibly diffuse gas spread thinly across the vast expanse of intergalactic space. Imagine just a few atoms, perhaps only 2 or 3, scattered across the volume of an entire living room. That gives you a sense of the extreme low density we're talking about. This elusive form of matter is called the warm-hot intergalactic medium, or WIM for short. And due to its unique properties, it's proven to be nearly impossible to see with conventional methods. It's a plasma, a state of matter where electrons are stripped from atoms, heated to millions of degrees Celsius. This extreme heat renders it transparent and ethereal, making it incredibly difficult to detect. The WIM barely interacts with its surroundings, further complicating its detection. Its diffuse nature and lack of interaction render it essentially invisible to traditional optical telescopes. The WIM does emit a faint X-ray glow, a potential signature of its existence. However, this faint glow is easily drowned out by the much brighter and more intense X-ray emissions from other cosmic sources. Therefore, detecting the WIM became a significant technological challenge, pushing the boundaries of astronomical observation. We needed instruments far more sensitive than anything we had previously developed. Instruments capable of picking up its faintest whisper of a signal amidst the cacophony of the cosmos. For decades, our existing telescopes simply weren't up to the immense task of detecting this elusive matter. And so, the missing matter remained hidden, a cosmic mystery waiting to be solved. It remained concealed in the vast darkness between galaxies, a silent and unseen component of the universe. Only with the advent of new, groundbreaking technology could we even begin to consider the possibility of finally seeing this hidden component of the universe and understanding its role in cosmic evolution. The universe's deepest secrets waited patiently, guarded by the limitations of our technology. But they waited for a new generation of cosmic eyes, for advanced telescopes capable of piercing through the darkness and revealing the hidden matter within. The breakthrough came in the Shapley supercluster, the largest concentration of galaxies nearby. Scientists targeted the space between two galaxy clusters, hoping to spot the elusive gas. Using the XMMM Newton X-ray telescope, they observed for over a week, collecting every faint photon. After painstaking analysis, they found it, a bridge of hot X-ray emitting gas stretching between clusters. This filament, though incredibly tenuous, contained enough mass to account for much of the missing baryons. The discovery was confirmed with Japan's Suzaku satellite. This wasn't a random cloud, but a structured filament, part of the universe's hidden architecture. The missing matter was there all along, hiding in these vast, hot, nearly invisible structures. The cosmic books were finally starting to balance. So what is a cosmic filament? Picture the universe as a three-dimensional spider's web. Galaxies are like dewdrops at the intersections. The strands are the filaments. These immense structures, made of dark matter and hot gas, stretch for hundreds of millions of light years. Filaments channel matter toward galaxy clusters, fueling their growth. Despite their size, filaments are almost invisible. Their gas is so sparse you'd never notice flying through one. Observing them is like spotting a faint wisp of steam against a cloudy sky. Their existence was predicted by simulations long before we saw them. Dark matter forms the core, pulling normal matter along and heating it up. Finding a filament confirmed our models of the universe's large-scale structure. Detecting a cosmic filament, a faint bridge of matter stretching across vast distances, required more than just a powerful telescope. It demanded a new way of seeing, a method to unveil the invisible. It needed special vision, the ability to perceive X-rays, a form of light far beyond what our human eyes can detect. The XMM Newton Observatory, a European Space Agency mission, with its massive, meticulously crafted mirrors, was designed precisely for this purpose. It gathered the faint X-ray glow, the whispers of energy emanating from the filament's hot gas, heated to millions of degrees. It stared at the same, seemingly empty patch of sky for days on end, patiently collecting the sparse photons, slowly building up an image pixel by pixel from what seemed like a mere trickle of photons, each one a precious messenger from the distant cosmos. But just detecting X-rays, these faint signals, wasn't enough to claim a discovery. Scientists had to meticulously analyze the data, ensuring that the signal truly came from the filament itself and wasn't simply random background noise or some other form of cosmic interference. They carefully compared the region of interest to seemingly empty patches of sky, regions devoid of any known sources, meticulously isolating the faint excess emission that hinted at the filament's presence. To further confirm their findings, they turned to Japan's Suzaku satellite, another powerful X-ray observatory. Suzaku was particularly well suited for this task, as it excelled at studying faint, diffuse sources of X-ray emission. Independently, both telescopes, XMM, Newton, and Suzaku, saw the same signal, the same faint glow in the X-ray spectrum. This independent confirmation was crucial, proof that the detection was real and not an artifact of a single instrument. This powerful combination of cutting-edge technology and painstaking technique finally revealed what was once invisible to us, hidden in the depths of space. The universe's hidden structures, the scaffolding upon which galaxies are built, were now within our reach, open to exploration. The cosmic web, once a theoretical concept, was finally coming into focus, revealing the grand architecture of the cosmos. Finding the missing matter in the Shapley filament was more than a solution. It was a triumph for cosmology. The lambda-cold dark matter model, our recipe for the universe, predicted this matter should exist as whim in filaments. Simulations showed where to look, but we needed proof. The discovery matched the model's predictions exactly. Location, temperature, density. It was like finding treasure where the map said it would be. This confirmation strengthened our confidence in the standard model. Now we can trust its predictions about dark matter, dark energy, and the universe's fate. One mystery solved, and our focus sharpens on the next. The filament's discovery lets us truly visualize the cosmic web, the universe's real structure. The web is a vast network of filaments, nodes, and voids. Filaments funnel gas and dark matter across millions of light years. Where filaments intersect, we find nodes, galaxy clusters, the universe's cities. Our Milky Way sits in a quieter suburb of this web. The web explains why galaxies cluster and why there are vast empty spaces. Gas flows along filaments, fueling star formation in galaxies. The web's structure was seeded by tiny fluctuations after the Big Bang. Seeing the Shapley filament was our first direct glimpse of this hidden architecture. We now know we live inside a universe woven from these grand, invisible threads. Why does this matter? Because the missing baryons are the same kind of matter we're made of, protons and neutrons. Finding them completes our census of the normal stuff in the universe. Now, we can trace matter's journey from the Big Bang through the cosmic web into galaxies, stars, and us. Before, there was a gap in this story. Now it's complete. The discovery shows that normal matter exists in different states, bright in stars, hot and diffuse in filaments. This clarity refines our theories of galaxy formation. Galaxies aren't isolated. They're fed by cosmic rivers of gas. Without this inflow, galaxies would have run out of fuel for star formation long ago. The filaments provide the mechanism for this cosmic refueling, solving a key puzzle in galaxy evolution. Solving the missing baryon problem is a testament to scientific curiosity and persistence. The discovery closes the gap between theory and observation, giving us a more complete vision of the universe. Now, we see the cosmos as an interconnected web, not just scattered galaxies. The cosmic web is the universe's skeleton. The hot gas in filaments is its lifeblood. With this mystery solved, we turn to even bigger questions about dark matter and dark energy, which make up most of the universe. By mapping normal matter, we can better understand the universe's hidden components. Every discovery brings us closer to answering, where did we come from? What is our place in the cosmos? The search for knowledge